Okay, thank you for coming, in spite of the fact that it's Saturday. I actually am against organizing events during the weekend, and once I said to colleagues that on Saturday I'm an Orthodox Jew and on Sunday I'm a devoted Catholic, but they didn't want to change the times of the conference. So I resume my lectures. Today I will talk about a way to model social networks using games. The reason I want to do it is twofold. One is to show you how certain mechanisms which take place naturally in social networks, one of them is diffusion, can be naturally modeled using game theory. And second is to illustrate another paradox. Yesterday we talked about the brass paradox, but there is a different paradox which is called paradox of choice, and it was discovered by a psychologist in early years of the century, and I'll show you how it can be naturally modeled in this context. So the purpose essentially of this lecture before the break is to show you versatility of strategic games, that they can model certain natural phenomena. And the differing feature of social games as opposed to the other ones is that these are not games where people compete, but essentially there is some element of coordination in these games. So you will see more as we progress. Yeah, so what are social networks? Everybody knows, but I have never given this lecture that everybody knows all the bullets. Now, you probably don't know what is Hives. It used to be in Holland the most popular website until all kids at school switched to Facebook because they all know English well enough and they had no problems with it. And then I think even I don't follow these things. I guess that Facebook now also is available in different languages. Nasza klasa I know by chance because, as I mentioned to you, the most important information of this lecture, I have a twin sister and she once told me, you have to register. So then there were some messages from people with whom we were at the same time at school more than 50 years ago. So you would think, how can one talk scientifically about these matters? Because this sounds like a topic in sociology, but this is not exactly the case. It is a very vibrant research area which spreads over several disciplines. So for example, in sociology, people study how certain patterns of behavior spread. And in economics, people want to understand better what are the effects of advertising, in fact, for bad reasons, because they want to improve effectiveness of advertising. So they want to know how it works, like advertisement by the word of mouth and so on. And in epidemiology, one studies how diseases spread. And this also has something to do with, obviously, with human contact. So it is a form of social network which underlies epidemics. In computer science, people use the tools which they develop to provide complexity analysis to these issues. And in mathematics, one considered already for a long time various structures which are the, so to say, backbone of social networks. So all these techniques somehow are useful when one wants to understand better what social networks are about. So I happen to be at my institute, have been ordering books for several years. Nobody wanted to do it, and I just completely differently like it very much. So at a certain moment I started to order books, and I stopped this list because it goes on, but it gives you some idea that there were books which started in 2004. So within few years, I remember at 2010 I stopped updating this slide. So This is roughly an idea to convey you the message that it is an interdisciplinary area, because several of these books, some of them are even in the title, fit in the economics, but some are in sociology. And in fact, this book of Easley and Kleinberg is a book written by an economist and a prominent computer scientist. And the last one is written by a physicist. So just to give you some ideas of what people study in this area. So one is in epidemiology, how the diseases spread. Viral marketing is how to make a product successful. So I remember ages ago there was, or there is still, I guess, such a singer Shakira. Does she still exist? So she got for free some new version of, I don't remember, Samsung smartphone or something like this in golden letters, and she got it for free. Now, why? Because it became a news item, and she posted this on Facebook. So this created some free advertising for the company. So this is called viral marketing, that you aim at certain people, and then you know, they wear the Rolex, for example. Every person who wins Wimbledon appears soon after in some glossy magazines holding his racket in such a way that you see his Rolex watch, and under it there is some advertisement of Rolex. So of course they get it for free. So this is called viral marketing. And there is also another topic I'll mention to you, which we studied, like a possible impact of a product if you introduce it. So let us be more specific. So here is a model which we introduced. It is a mathematical model which tries to capture some aspects of social networks. So we have a weighted directed graph, and the vertices of this graph are agents, so the people who form the network. And an edge indicates a connection, that somebody, if there is an edge from me to you, it means that I know you. So these edges are directed. And we also have a finite set of products. And then there is some assignment of products which you can buy. So each agent has a certain set of products he can buy or she can buy. And these can be different things. For example, if you buy a computer, I wanted once to buy a new laptop, so I started to study the prices, and then I see it's cheaper on Amazon in Great Britain, but it's written unavailable for people outside of UK, because they had some special deal probably. I also have some books on which it is written not for sale in US. So it is, some products are available only in certain countries. So we model it by allowing different sets of products available to different agents. Now there is also a resistance to buy, but you can, it is usually called threshold, and such models are called threshold models, but you can equally well view this threshold as a price of this product. So the theta IT is a price of the product I price of the product T for agent I. And we just normalize it, so it will be between 0 and 1. So all what we need to know is that neighbors are people whom I can reach directly, and source nodes are people who have no friends, who have no people, I'm sorry, I should correct myself, that the neighbors are people from whom there is an arrow towards me. And some people are influential, so they are the source node, the beginning of the whole story. So now I will discuss the crucial concept of a diffusion, how things spread in a network. So initially we assumed that no node adopted any product. This is an initial situation. And then the source nodes can adopt a product from their list spontaneously. And diffusion is a kind of cascade which percolates down this network under certain assumptions. So the assumption is that if I am influenced sufficiently by my neighbors, then I can adopt the product. So the precise condition is that this is a weighted graph, and a weight indicates how much I am influenced by a specific person. The higher the weight, the more influence this person has on me. So for example, your close friend will have a very high weight, whereas your parents will have minimal weight. Yes. So now we consider a given agent and a given product, and we now think, can he adopt this product? So the answer is, let's see what happens to his neighbors. So we add up the weights of these neighbors. So it is an aggregated weight, and these weights should exceed the resistance to adopt this product by this agent. So you can equally think that this resistance is the price, so that this weight somehow provides an evidence for a person that he should buy this product, and it should exceed the price of it. Now, I can give you a good example of it, which happens really, that people have to decide which provider for their smart telephone, mobile telephone they want to adopt. Many companies make it for you attractive if you adopt their subscription, because then you can call for free people who also have the same subscription. So if you have many friends who have chosen the same company, then you are tempted to choose it. But of course, it can be that 40% chose one, let's say, provider, 40% another. So now, of course, the issue is not the numbers, but the accumulated weight, because with some people you talk more often than with the others, and it is an evidence or some incentive for you to adopt this product. But it has to be, this incentive has to be bigger than your resistance. So this is this equation. So in this sum, we sum over all your neighbors who already adopted this product. So this is this expression n with at the top the product and at the bottom I, because we talk about agent I. And once you adopt this product, it's final. And you can again ask yourself, does it make sense? Well, in many cases, yes. For example, in the Netherlands, it is very rare that you change your bank. And the reason is that you have all sorts of subscriptions and automatic transfers which are attached to your account, and it is extremely cumbersome and problematic to move to another bank. So they even start some campaign that we will provide you with all the changes. It never works, I heard, and people in general very rarely do this. So it is extremely important for a bank to attract a customer, but once he's already in, that it's a very rare situation that he will change. The same with, I don't know, suppose that you consider where to go to school. So children in primary school, I still remember in my own family case, that where to go to secondary school, those kids don't listen to parents or to teachers. They just check what the friends decide. So this is and if some friends said, yes, I go to this and that school, then it is a huge incentive for a child to move to this school. But once he does it, it's final. So here is an example of such a network, and I will give you on this running example, provide you an illustration of diffusion. So suppose there are three possible products. There are those bullets, red, green, and blue. And this is a weighted graph. Now these weights indicate how much agent influences the other. And so there are 6 agents, and let us assume that the threshold is 0.3. So now there are 3 source nodes, and they have actually only one choice. So we can now study how the diffusion happens. So, for instance, this situation is one of the possible effects of a diffusion. So let us see what happens. Those source nodes adopted the product, I mean, I will talk about colors now, adopted the colors which belong to their set of products. There is no choice there. But then the internal 3 nodes adopted things only on the basis of what their neighbors adopted. So for instance, node 1 adopted red. It could have adopted blue in principle, but it adopted red. And why could it adopt? Because the threshold is only 0.3, whereas the weight is 0.4. So this accumulated weight, which is 0.4, is bigger than 0.3. So this subsequently was adopted by node 2, and also node 3 became blue for reasons as you can imagine. So now this is a final situation. This is an effect of diffusion. Now we can ask ourselves, how much time did it take? By time I mean how many, so to say, rounds. So just a small observation and good test whether you follow it. So I claim that this situation can arise in 3, 4, 5, or 6 steps. Yes, and let us see how can it arise in 3 steps. So in the first step, the source nodes will adopt 3 steps. It has to go fast. Yes, so the source nodes adopt the color. It is not necessary because in per round, it can be already very slow that only one node adopts a color. So first the source nodes, then what can happen in second round, which, I mean, we now try to proceed fast. So which nodes can become colored in second round? There are 3 nodes left, yes, the internal nodes. So according to this diffusion definition, which nodes will be colored in round 2? Any? Well, not exactly. Sorry? But 2, can 2 be colored in the second round? Exactly. The problem is that 2 has 2 neighbors, namely 1 and 5. So it could become either green, because then it would be on the basis of influence from node 5. It could also become red as it became on the basis of the influence from node 1. But node 1, after round 1, was not yet colored, correct? So what I mean is that node 2 can be colored at the earliest at stage 3. So this shows why it has to take place at least 3 steps. And if you slow things down and in each round one node adopts a color, then there are 6 nodes, so it will take 6 rounds, and you can find any number in between. So this is the process of diffusion. I only show the final stage, but I will return to this example. Are there any questions on this? No? Yes. Yes. One moment. Why is 3 blue? Because, good question. The point is that 3 has 2 neighbors. Each of them can influence it, but the node 3 does not have color red in its choice. So it can only become blue or green. And it could become green if node 2 became green, but node 2 didn't become green. So is that your question? Yes, the source nodes, yes. Yeah. In the second, it will be node 1 and 3. And 3 will be colored because it has a blue neighbor. Correct. So 2 will be colored in the third round. It could, but it doesn't have to. That's the point. So good that you asked. The point is that there are many possible scenarios. It is just one scenario. One could equally well have a scenario that 2 becomes green and then node 3 becomes green. So it is not unique. It's non-determined. The outcome is non-deterministic. No, as soon as this threshold is exceeded by some combination for certain color, then it can adopt it. It doesn't have to wait. So intuitively, it is as follows. Let's suppose people decide to buy their mobile phones, the subscriptions, and then they don't wait till they learn about each of their contacts, what they did. As soon as there is compelling evidence to choose a specific provider, they just can do it, but don't have to. So it is one of many outcomes. Yes, sure. No, this is a possible scenario. So the node 2 can also become green. It is a possibility. This is not a unique outcome. Yes. Yes, he's right from the, yes, at the second step already he can choose a color. Correct, but he was lazy, so he chose it at step 3. Exactly, yes. So this is a possible scenario, but it's a final. So you should think that there is a tree of possibilities. It is one of the leaves in such a tree. So you can ask yourself various questions. I'll just give you some examples, what we studied, that you can get an idea where such model can lead to and what has it to do with computer science. So you can have such a network and suppose that you have a fantastic product, let's call it top, and we want to figure out what is the minimum amount of agents who will adopt this product. So suppose that you have a manager of a company which is responsible for production of this product top, and he's extremely cautious or pessimistic. So he wants to investigate what is the minimum that they will provide, they will succeed to sell. So this is what we call min adoption. And max adoption is the other way around. It's an optimistic young manager says, we can sell it under best circumstances, and that is the amount we can sell. So now the question is, given a network and such a product, compute both of these numbers. Now, there is a story which I should illustrate that it is not so simple. It's a very old story which I read somewhere, that it was still during communist times. Some Yugoslavian company sent 2 representatives to Africa to investigate whether they can sell their shoes. So one representative came back and said, it's a fantastic market. We really can sell a lot of products because many people walk here barefoot. So there came another representative back and he said, it's not a promising market because many people walk here barefoot. So this just shows that it is not so simple to, let's say, draw conclusions. So here we want to compute these numbers. So I will not discuss the details because it's not game theory, but I'll just tell you that this max adoption is a simple problem, and this min adoption is very complicated computationally problem. This max adoption can be done by pushing first only product top. So this allowing all the other products, just trying to flood the network with this product top, see what happens, and then complete the diffusion process. So it's a very simple algorithm, but with the other problem, the min adoption, it can be solved efficiently still for 2 products, but for more it is really a complex problem. So it is even difficult to approximate it, the correct answer, with some good precision. But this is just to give you an idea what type of questions one can ask and how come it leads to computer science. But now I will go to game theories. I will associate with these social networks games. So no surprise, the players will be the agents and strategies will be the products. But we also have to model the fact that an agent did not select yet a product, so it will be T0. It's sort of this initial situation that an agent did not adopt a product. And we assume also some number which will be just a payoff, so the value of a product for the source nodes, because they just can adopt any product from their set, but I mean, how much do they gain? Now, we want to model this problem of resistance in adopting products, and this will be incorporated in the payoff function. So if we have a source node, and it did not yet choose a product, so its strategy is T0, that is the way we model it, then we assume the payoff is 0. If it adopted a product from its set, then it always gets the same profit, C. You can have different profits for different products, but then when studying Nash Equilibria, you always choose choices where the players don't regret. So they will always choose the best product. So it's equally, without loss of generality, let's assume that all the prices are all the costs are the same. So this is the profit for source agent. Now, if it is not a source agent, then we model its payoff using this equation which we saw before. So if a node adopts a product, it has not yet adopted a product, then its payoff is 0. And if it adopts, then we look, because we now study payoff given what everybody chose. So we now look which product this node adopted, and for this node we check what the neighbors adopted, we select those neighbors who adopted the same product, we add up their weight, and we deduct the price of this product or this resistance to adopt. So this is this crucial formula here. So here at the bottom, we sum up the weights coming from all the neighbors who also adopted this product, and we deduct the price of this product. So to summarize, this is the crucial line. If node I adopted product T, in other words, if we have this Si equals T, then the payoff for this agent is obtained by adding up the weights from nodes, neighbors who also adopted the same product, and we deduct the threshold. So here is an example. Here we have this familiar already network, and now suppose that this is the configuration which we consider, which now is a joint strategy, correct? So I want to check what are the payoffs here. So according to what I just showed, the source nodes, the payoffs for them is C. They adopted a product, otherwise it would be 0. Now, what would be the payoff for node 2? Or for node 1, perhaps. Let's start with according to the formula. Do you remember still the formula? But it's still here very easy. So how do we compute it? We look at neighbors of one who also adopted red. Now there is one neighbor, correct? And what is the weight coming from this neighbor? 0.4. So from 0.4 we deduct the threshold, we get 0.1. So this is how we got the payoff, yes? Clear? Okay, so now we still have to complete. So this is how the payoffs are for the other nodes. Do you agree? So for example, for node 3, which is blue, it has an edge with weight 0.4 from a blue neighbor. So it's 0.4 minus 0.3, correct? Okay, so this is a game. And now, what are the characteristics of such games? So first of all, it is something called graphical game, that the payoff of each node depends only on the strategies chosen by its neighbors. In general, you may depend on all the other players, but here this graph determines on whose payoff on whose strategies your payoff depends. And another property, which we call join the crowd property, is that the more people adopt your strategy, the better for you. So this models this effect of joining the bandwagon, it's called in English, that if people behave like you, then it's good for you. So these are two characteristics, and this last one is exactly what does not happen in Prisoner's Dilemma, in Tragedy of Commons, in what was the other example, this public goods and so on. So these are different games. They have a different flavor. Congestion games, that's what I meant. So now a good question is, do these games have Nash equilibrium? So the answer is, let's look at this game. So first of all, if we try to find Nash equilibrium, obviously each of the source nodes has two strategies, but it's better to choose a color than not, because then the C payoff is strictly positive. So we only need to worry about those nodes in the middle, these three nodes, and the question is, can we complete the coloring in such a way that everybody is happy? So I know that it's a very dramatic question, so I can't let you wait. So, for example, is this a Nash equilibrium? So who is not happy? Exactly, because the weights on the internal triangle are higher. Correct. So he's not happy, so he should choose to red. And it goes on this way. So we get such a cycle. So this configuration which I mentioned would change to the one above, which is blue, red, blue. I only mark the internal nodes. So the node, which one? Here I just chose node 1, which is not happy. So chose node 1 is not happy, it changes to blue, and this continues this way. And these are not all configurations. I had no space here. There are in total 8 configurations, correct? Because there are 3 nodes and each of them has 2 options. We talk about nodes 1, 2, 3. 1, 2, 3, yes. So these are 6 configurations, but there are still the missing ones are that each of the nodes chooses a different color. And the arrow is this improvement path step. So what you see here, this cycle, is an infinite improvement path, which is illustrated by the fact that each such triple represents a given joint strategy, because the source node's assignment or selection is fixed, and each differs from the previous one by just one player who change a color, and it becomes a cycle. And those 2 missing ones are configurations which, so to say, end from which there is one step into this game, so into this cycle. So the net effect is that this game will have an infinite path, and there will be never a configuration that everybody is satisfied. So the conclusion is this game has no Nash equilibrium. So here the intuition is that these nodes internally prefer to adopt the color of a predecessor, but they do not have all the same colors. So as a result, it keeps changing, because there will be always somebody who would like to select the color of the predecessor, but then he affects his successor. In short, there is no Nash equilibrium in this game. So now you can ask yourself how difficult it is, given such a social network game, to decide that it has a Nash equilibrium. So this problem turns out to be NP-complete. And now I'll give you some proof, which I hope will be readable enough. We use a reduction from one of the first problems which was identified as NP-complete, called the partition problem. So the problem is that we have n rational numbers which add up to 1. And the question is, can you divide them into 2 parts, partition into 2 parts, such that each part adds up to half? So this is an NP-complete problem, and will provide reduction from this problem. So we have an instance of partition problem, and I will now construct a social network such that there exists a solution to this partition problem if and only if the social network has a Nash equilibrium. So we create 2 copies of this network, which you already know. And the one on the right has new nodes, so they are all primed, but also new colors. So the colors also have a primed version. Then we add at the top n new nodes. N is the number which is available from the instance of the partition problem. And we create links from the first node, this additional node, to these nodes 4 and 4/2, for prime, and so on. So now we have to, we had weights already in this initial small graphs. But now we added edges, so I just have to decide what is the threshold. So the threshold here will be always fixed, does not depend on the choice of the product. So for node 4, it did not have to have a threshold before. It was a source node, but now it isn't anymore. So we have to equip it with a threshold, and the threshold will be half. So now what we have here is the following situation. Suppose I have a solution to this instance of this partition problem. So I have these numbers A1 to AN. Sorry? No, this is exactly the important issue. So we now make the following decision. Suppose I have a solution to this partition problem, which means that there is a subset of these nodes I1 up to IN, such that these weights of coming out of these nodes add up to half. So for this subset, I say all these nodes adopt red, and the other nodes adopt red prime. Now, once this happens, I now have the following situation, that nodes, the sum of the weights coming from them is half. These nodes adopt let me repeat. The I nodes which adopted red, the sum of the weights adds up to half. Now, for these nodes, I now claim that node 4 can refrain from adopting a product. Because what happens? If it adopts red, then what is its payoff? It is half on the positive side because the edges add up to half, the weights. But we have to deduct the threshold, which is also half, so it's 0. So this node can adopt T0 equally well. There is, in short, it can adopt the strategy T0 or simply refrain from choosing a product. The payoff will be also T0. It is not anymore a source node. So I have to use this complex formula for its payoff. And the same with the node 4 prime. Now, why is it relevant? We broke this vicious cycle in these lower networks in which there was no Nash equilibrium. Once you decide that this node adopts no product, you can complete it into a Nash equilibrium because you simply start coloring things by adopting informally diffusion from nodes 5 and 6. And this will not conflict with the pressure which node 4 exercised on node 1 by having adopted red. It adopts nothing. So this I can complete to a Nash equilibrium. So this shows that in one direction, this implication holds. If the partition problem has a solution, then I can construct a Nash equilibrium. In the other direction, it is also the case because we have the converse implication as well. Why? Because if there exists a Nash equilibrium in this network, then necessarily in this Nash equilibrium, node 4 and also node 4 prime adopted the strategy T0. Because if it adopted red, for example, node 4, then we would have this vicious cycle which we saw before. Which means yes, that's very important, yes. So because we proceed now in two steps. There is a Nash equilibrium. From this we conclude that in this Nash equilibrium, nodes 4 and 4 prime necessarily chose T0. Now, if this is the case, then it means that for each of them, the payoff cannot be worse than adopting red. As a result, for each of them, the pressure from these I nodes choosing red, for example, for node 4, cannot be larger than adopting 0. In other words, payoff for this node for choosing red is not bigger than 0, which means that this number of nodes which adopted red in the Nash equilibrium in this I list is at most half. And also for the other, for 4 prime, it's also at most half. And it adds up to 1, all these weights, so it means it's exactly half. So from this we conclude that these nodes, I nodes, some selected red, some red prime, but in such a way that these weights add up exactly to half. You can see the precise argument in the paper, but this is the idea of the proof, and I hope at least you understand the main steps. So we have also have to check how big is this network. The input was of length n, but this network is n plus 12, so it is linear in the input, so there is no problem here. So the conclusion is that this problem is NP-complete. Now I am slightly late, so let me mention that we have this Nash equilibrium problem, but it turns out that if we had 3 products, 3 colors. Now, if there are 2, then you can always find a Nash equilibrium. So to find a counterexample, you need at least 3 products, and the intuition behind this result is very simple. If you have 2 products, suppose that they are blue and red, then you first push product red as much as possible, and then you just push product blue. And this turns out to be Nash equilibrium. So it is a very simple construction. Yes. This I don't know, but I have the following observation here, that it contains a cycle and it contains source nodes. And now we can ask ourselves, are both assumptions necessary? Whether my suspicion is that it is the closest, because for a cycle, I'll show you there is an obvious Nash equilibrium, and if there are no source nodes, then there is also a Nash equilibrium. So you have to have both a cycle and source nodes. So I think that it is difficult to come up with smaller. But you can ask yourself a question, does a Nash equilibrium exist when the graph is acyclic, so does not have a cycle, or it has no source node? So you can study these questions, and some of them are stupid, because if, for example, take a cycle, obviously it has a Nash equilibrium. And you can tell me what is the Nash equilibrium in a cycle. You are allowed to look at this slide. Sorry? I'm sorry?
If there's no source node, then everybody has to choose.
Bravo. And this is a Nash equilibrium. So everybody chooses, decides not to choose. Look, if one person changes its mind, and because it says I'm not satisfied, then he will be the only node which chose a color. So of course his payoff will be negative, because there will be no edge coming into it from a node which chose this color. So his payoff will be the threshold, but with minus in front of it, which is worse than 0. So for such situations, you have to talk about a more demanding type of Nash equilibrium, where at least one player chose a color. So in a DAG, so directed acyclic graph, such Nash equilibria always exist. It's very easy. You just tell the source nodes to choose some color, and then you just push it down, and this construction ends because it's an acyclic graph. So you just propagate it down the graph. And you can also study the question of graphs with no source nodes. So there you get a reasonable algorithm which can determine whether in such a graph you have a non-trivial Nash equilibrium. And again, the construction is not complicated. You speculate which color it could be. So you choose some color, you push it maximally through the network, and you complete it with T0, and you check whether this is a Nash equilibrium, and you do it for each product. That's why there is this cardinality of the product in this complexity. So what I am trying to convey to you is that these games which we started to model social networks have different behavior than the games which we studied so far, because very simple examples of games have no Nash equilibrium, but in many cases they are, and we can also determine in some situations in an efficient way whether Nash equilibrium exists, but in general it is NP-complete. So I want to check what is the situation. So now I want to compare the notion of improvement path with the diffusion. So this is just a reminder in case you did not, you were too tired yesterday. So when players are not satisfied, they choose a better response. So a joint strategy moves to another version where only one player changed the strategy. We call it a profitable deviation. And then improvement path is just such a maximal sequence of profitable deviations. And as I mentioned yesterday, a game has the finite improvement property if all improvement paths are finite. So now let us look at this diffusion process, which was at the beginning. I can, in some sense, model it using the improvement path. Namely, we assume that it starts at the initial joint strategy where nobody chose any color. And so everybody's strategy is T0. And then we assume that each player can change strategy only once. And as a result, this diffusion process will now be will consist that one or more players change the strategy, and this will model in an improvement path where only one player can change strategy by serializing such a change, and by therefore this change can take place simultaneously, but we will, so to say, if there is an instance of diffusion, you can model it by this improvement path by serializing it. And therefore, if we disallow that nodes change a color after they adopted one, then we necessarily have a type of improvement path which ends, and this will be a modeling of diffusion. So the message behind this slide is that the concept of diffusion, which had nothing to do with game theory, can be retrieved in this framework. So I just want to give you some examples of results which we obtained, just to give you some idea, and also to mention I always have this bad luck that whatever I work on, there are various results, and there is always one we cannot solve. So in this paper, there was this question mark, and it always bothers me when you cannot complete some study. So I will explain to you this open result. For the other ones, you can just look at it. So there is the finite improvement property, which already yesterday was mentioned, today I mentioned again. Suppose it's a very simple problem. Suppose that you have a simple cycle, a special case of a directed graph with arbitrary weights. And you ask yourself, is this instance of a social network game such that it satisfies this finite improvement property? And the question is, what is the complexity of deciding this? And we don't know. And if you assume that people change a strategy only to the best response, so this is finite best response improvement property, this FBRP, then we have the answer. But if you do not insist, we don't know. So these are results which show that things vary from NP-complete to linear to co-NP-hard. So there are several options and it depends on the structure of the graph. You don't need to remember it, but just it is to give you an idea what type of research one can do. And these are the explanations, but it is not relevant. It is simply to give you a sort of an idea what type of research we do. So now I will discuss a paradox which was identified by a psychologist, and it is a very influential paradox. It even has a page in Wikipedia, so nowadays it doesn't mean much. And this is a book which was quite important because it was the first evidence that this affluent society in which we live causes problems. And there is a book by a German psychologist, Giger Renzer, who provided, called Gut Feelings, who provided, in my opinion, a very good summary of this paradox. So he wrote the following summary of it. The more options one has, the more possibilities for experiencing conflict arise, and the more difficult it becomes to compare the options. There is a point where more options, products, and choices hurt both seller and consumer. In other words, if we have too many choices, it is not good for us. And actually, people now say that the young generation, millennials and so on, so forth, have a problem because they face too many choices. And in Amsterdam, I noticed that it manifests itself in a really difficult decision for children who finish secondary school, which studies to choose. And because there is such an enormous amount of options, and during each study, there is only, say, half of obligatory subjects, and you can choose the other one, so people really don't know what to do. And this becomes a source of tension and anxiety, and when we think about it, my generation didn't have that many choices, and perhaps life was simpler. So I want to show you that this paradox can be formalized, or by rather illustrated. And an example is, in Holland, they liberalized the energy market. So there was only, I think, one company at the beginning which provided energy. So essentially they had monopoly, but then according to European Union rules, it is not legal. So they opened the market, plenty providers showed up. So there were huge lists and you had to check and make choices. And then I read with my amazement that 93% of people remained with this main provider. So this competition only convinced 7% of people to switch. And the same is with medical insurance. There, it's always a headache each year what to do because the prices change, and then there are some long articles, website comparing, and you have to figure out because it depends what they offer, and each offers something slightly different, and you have a problem. So this problem is because there is an abundance of choice. So this is one version of this paradox. I'll show to you that if we add a product to a social network, it can trigger a sequence of changes which results in a situation where everybody is worse off than at the beginning. So we will have initially a situation where everybody is satisfied, read in brackets, it is a Nash equilibrium. Then a product will be added. This will unavoidably trigger some sequence of changes, and at the end, everybody will again be satisfied, but everybody will be worse off than at the beginning. So here is the network. So we have a very small threshold. So this threshold will not play any role in the arguments. So if you look at what happens here, then you can easily see that these nodes are paired and each supports, so to say, the choice of the other one in a horizontal way. So this is clearly a Nash equilibrium, and you can easily see, for example, node 3 has both a neighbor, two neighbors, each of them has influence 0, 1, but it's enough if you have one neighbor who supports your choice. You choose a color because 0, 1 is bigger than the threshold. Correct? So this is easy to see. It is a Nash equilibrium. Everybody made the right choice. Now suppose that we add to node 4 a new alternative, blue. So now what happens? Is this a Nash equilibrium? I say that it's not. Which node is now not satisfied? Exactly. Why? Because it could switch to blue, correct? Because blue is adopted by node 6 and the weight from node 6 is 0, 2 and not 0, 1 as the weight from node 3. So it adopts color blue. Now this is again not a Nash equilibrium. Any suggestions which node is now not happy? 2, correct. But I change it to, I now decide something else. I make a choice that node 3 changed. It was blue before, but now, sorry, it was red before. I have to go back. Oops. This was the situation. So this node changed to blue. This one is red. Nobody is red, so it's bad for him. It chooses green. And now this is the order is important. So now node 5 changes to green because this arc, this edge has weight 0, 2. Now we change node 6 and the color gray indicates T0. Now why is this an improvement? Because look what happened. Node 6 had color blue, but node 5 is not anymore blue. So at this moment the payoff to node 6 is negative. It is minus threshold. So it changes to T0 because it's better to choose nothing than blue color. So in that case, it becomes T0. And now this T0 will propagate everywhere. But before this, I make this node blue. It is a good decision for node 2 because the weight is 0, 2 as opposed to the previous color green, which was supported only by weight 0, 1. And now from this moment on, this T0 will percolate through the network because now this node lost its support, so it has to choose T0. Now there is a problem with several nodes, 3 and 4. I don't remember which one. 4 will now change to T0. Now both 3 and 2 are in bad shape, but I don't remember. 2 now changes, now 3, and now 5. And this is a Nash equilibrium. So what happened? We added this blue product in a situation where everybody's payoff was strictly positive because the threshold is very small. It's below 0,1 and 0,1 is the minimum payoff in that initial configuration. We added this product and it triggered a sequence of changes which we modeled by an improvement path, and this improvement path ended up in a very bad Nash equilibrium. This Nash equilibrium was also present in the beginning because somebody noticed here that if everybody chooses T0 in such a graph when there are no source nodes, then it is a Nash equilibrium. But it was not the initial situation. So this is something similar to the brass paradox, but it is a different setup. In brass paradox was concerned with congestion games, and there people compete because if somebody chooses the same road as me, it's bad for me. Here it is the other way around. If somebody chooses the same product as me, then it is good for me. This is this join the crowd property. So in this setup, also such a problem exists. And again, I mentioned to you, in each paper I wrote, there is an open problem. So here is an open problem for you. You notice at certain moment somebody said, oh, now node 2 is not happy, but I changed node 3. It is not accidental, because here the situation is that there are some paths which do not lead to bad situation. The problem is there is a path which leads to bad situation, but not all of them. So the question is, does there exist a social network in which we can manufacture this paradox in such a way that this bad Nash equilibrium always will be generated and not by some path. So this is an open problem, and this is at the end I will show you. Now I have still a little bit of time before the break for a much simpler paradox, which is that if you remove a certain option, it's good for everybody. So it's a kind of reverse, that you limit the number of choices and it becomes a good change. And it's a very simple example, so it's good just before the break. So we have a situation of a very simple graph. The important thing to notice is that in this graph everybody has two neighbors. And there are only two nodes, 3 and 4, that have different options. So it is, the weights are just bigger than threshold. That's all what one needs to know. So this is a Nash equilibrium. So two nodes chose blue and two nodes chose red, and the point is that they support each other, so the payoff to each node is 2 times weight minus threshold. Now we remove a product, but now comes a problem. We have to decide what it means. We will remove product red from the set of products of node 3. Now this creates an illegal situation. So the first thing is to restore it to a legal situation. So the node 3 will have to move first to a legal situation. So we remove this color. So as I said, it's not a legal joint strategy, so we just say it has to change. So for example, the only change in this case is that it has to withdraw from a selection of a product. It has to adopt T0, this gray color. Now this is not a Nash equilibrium. I'll just easily, you can see that node 4 has to change now, and this can change now in turn to blue. And from this moment, it is not a Nash equilibrium because this one can also change to blue, and this is a Nash equilibrium. So now everybody has blue. I said it wrong before. The payoff in the initial situation was omega W minus theta, where W is the weight. because everybody had one neighbor who adopted his color. Now, since everybody has two neighbors and everybody adopted the same color, so the payoff now increased to 2 times W minus omega, minus theta, I'm sorry. So what happens here is that the payoff went up. And here, in contrast to the previous paradox, it is the case for every improvement path. I just showed you one where this node 3 was resistant to adopt blue color, but still then it in the end had to adopt. So here, all the paths lead to the situation that everybody adopts a blue color. Therefore, all paths lead to a better Nash equilibrium. So this is an easy paradox. This we constructed in few minutes. The first one we had quite a hard time. So now some open problem. So I mentioned this open problem, but I'll tell you that this bothered me so much that we came up with a study of it in a different setup where one did not have T0. So like you would say that this models a situation that each child has to go to secondary school, yes? That there is no option of not choosing a school. In that case, we have a positive answer to this problem. And I feel very proud because I constructed this example by a mixture of reasoning and programming. So I sort of speculated that the network is of that shape and then wrote a program, what are the conditions for the weights and for the thresholds. And lo and behold, there was a solution for it, and this way we obtained the right network. So to summarize, when the adoption of the product is obligatory, we have a positive solution to this problem. But in the setup I explained throughout the lecture, we don't know. So to summarize, the open problem is, can you create a network such that an addition of a product into this network unavoidably will move players from a given Nash equilibrium to a worse Nash equilibrium? So this is your homework. Okay, so thank you for perseverance. So now this remaining lecture will be devoted to explain to you the fundamental results of Nash and von Neumann. It was first von Neumann, as I mentioned, who established important results, but it's better to look at it from the current perspective where we understand the general picture better. So I'll start with what Nash proved, and then I'll explain to you what von Neumann proved. So we start with exposition of a Nash theorem. So first I have to be a bit more precise what are mixed strategies. You remember them perhaps from the first lecture. It was a bit informal. Then I will make it more precise what is this mixed extension of a finite game, and we'll discuss the Nash theorem. So let's go back to this battle of sexes game. So suppose now that we play it in a different way, that we allow probabilities, and this first player chooses fight with the F with probability half, and the other with probability half as well. So we write such a strategy as such a simple expression, half F plus half B. And suppose that the other player, the woman, chooses F with probability 1/4 and the B ballet with probability 3/4. So she also has a strategy, and we call these strategies mixed strategies. And to distinguish it from the previous strategies, which I used all the time, then the previous strategies will be now called pure strategies. So now suppose that each of them chooses this strategy, which is mixed now. So we have to define how the payoffs are defined. And for this we use this original matrix and this matrix of probabilities, and from this we can easily compute the payoffs. In fact, it is a multiplication of matrices, but I'll just write it out. So M is the joint strategy consisting of these two mixed strategies. And I want to determine what is the payoff for the first player, the man. So I go through all the 4 squares of the game, and for each square, I first check what's the probability that the game ends up there, and pick up the payoff. So the probability that the game ends up in FF is 1/8, because it is 1/2, that's what the man chose, and 1/4, that's what the woman chose. So the probability that the game will end up there is 1/8. Now we calculate the payoff for the first player, so his payoff there is 2. So I have the first term 1/8 times 2. And then you do the same with the remaining 3 squares, and you add it up, and that's the payoff. And now we do exactly the same exercise for the other player, the woman. So for instance, for a change, consider the last term, which is 3/8 times 2. How did I get it? Well, I took the probabilities, and the probabilities are actually in this table at the left, but it comes from the fact that the woman, for BB, the chances that it ends up there is 3/8, because it is 1/2 for the man and 3/4 for a woman. You multiply, you get 3 times 8. We now calculate the payoff for the woman, so it's times 2. So this explains the last term in this payoff for the second player. So these are the payoffs. So I hope that this example is clear enough, and now I'll just give you a formal definition. So the formal definition allows arbitrary strategies, arbitrary probabilities, and the rest just follows by exactly the same route. So mixed strategy for a player I is a probability distribution over his set of strategies. So this is the notation is delta of A, where A is the set of strategies for him. So each player now chooses a mixed strategy, so a probability distribution over his strategies. We form a joint strategy. It will be a joint mixed strategy. Now M, which has n entries, for each player a mixed strategy, and we want to determine what's the payoff. So the payoff is obtained by this formula. So given a joint strategy S, we calculate what's the chance that the game ends in that strategy. So we calculate the probabilities for ending up there for each of the player. So player 1 selected strategy S1. That's the entry of the joint strategy S. So we pick up, we focus on this very joint strategy S, like 1 square in this previous example. We take strategy S1, we calculate its probability. That's what the mixed strategy tells us. So it's M1 times M1 of S1. And we multiply it by the chance that we end up in this square given what the player 2 chose. So it is his strategy, which is M2, applied to the second entry of this joint strategy. So this way we obtain a product of n numbers, and this is the probability that the game will be played in this joint strategy. So for player I, we make a sum over all joint strategies. For each of them, we calculate the probability, and we multiply by his payoff for this joint strategy. It's exactly what I illustrated at the picture before, but just written down now formally. And if I only show this, I suspect you would get lost, but the intuition is in this example before. So the theorem of Nash is that this game, so constructed, always has a Nash equilibrium. And it is a very important result. It revolutionized, I never know how to pronounce this word, game theory. And as I said, he proved it, I think, when he was 21. And the proof is 1 page long. But his way of writing proofs was different than we are accustomed. In fact, in the text, there are hardly any formulas. As you will see, I will show you the paper in a moment. So it's a 1-page paper from 1950. And the example which I just illustrated already before is that, for instance, in the matching pennies game, there is a Nash equilibrium in mixed strategies where everybody chooses each strategy with the probability half. Now, in the case of the battle of sexes, there is also a mixed Nash equilibrium in mixed strategies. You will find the calculation in the lecture notes, and one can check that this strategy, where the first player, man, chooses fight with 2/3 and 1/3 the ballet, and with the woman the other way around, forms Nash equilibrium, and the payoffs for each of them are 2/3 in this Nash equilibrium. It is an issue how to check that something like this is a Nash equilibrium, so we'll come back to this in the following lemma. Because, look, until now, all the examples had finite set of strategies, all players. So if I ask you, is this Nash equilibrium? Then you simply had for each player to check whether he was satisfied. For this, you could simply look at all his alternatives and for each of them check that he was not better off. But if the game is infinite, then you can't do this. So the question arises, can you do it in a finitary way? And the answer is yes. And this is the lemma which provides a basis for it. So this lemma says the following. Suppose that we have a Nash equilibrium in mixed strategies. If I say, like in this battle of sexes, this is a mixed a Nash equilibrium in mixed strategies. Let's go back to this. To prove it, I would have for both players consider all alternatives, and for each alternative establish that he is not better off in this alternative. But there are infinitely many strategies, so I cannot do it in some naive way. And this lemma tells us you don't need to consider deviations to arbitrary alternative, only to alternatives which are pure strategies. And this is this equivalence. So M is a Nash equilibrium in mixed strategies. I wrote it out explicitly. It means that for all players, I will not get better off by choosing a different strategy M prime. This statement is equivalent that for all players, they will not get better off by switching to a pure strategy. This is a statement in the second bullet, because what happens is that we consider this inequality, but for only a finite set of deviations, namely to pure strategies. So this is a very useful lemma, and this lemma is easy to prove, but I have no time to study to provide you with the intuition. It's all in lecture notes, but it has also a very useful consequence. Namely, once we study a mixed extension of a finite game, we have new set of strategies, we have a new game. Now, can we recover the old game from it? Yes, because every pure strategy is a special case of mixed strategy where you put all the weight on this strategy. You put 100% on this strategy and for others 0. So every pure strategy is a special case of a mixed strategy. So now you can ask yourself, suppose the initial game has a Nash equilibrium. So in the new vocabulary, suppose that there is a vector of pure strategies such that in the initial game it was a Nash equilibrium. Is it a Nash equilibrium in this mixed extension? The answer is yes. And why? Because of this lemma. Because this lemma says, just check deviations to all pure strategies. But this we already know that these deviations will not yield any improvement for any player because we started with a Nash equilibrium. So this lemma is useful for two reasons. One is to check whether a purported Nash equilibrium in mixed strategies is indeed a Nash equilibrium, and the other, it allows us to ascertain that a game in mixed extension has, so to say, inherited the Nash equilibria from the original situation. So, for example, in the case of Battle of Sexes, we can state this game has exactly, in mixed extension of this game, has exactly 3 Nash equilibria. 2 are in pure strategies and 1 is in mixed strategies. Okay, so now there is a theorem which Nash used, which was established by a Japanese mathematician during the wartime, and he established a fixed-point theorem. Fixed-point theorems come in many flavors. This one is the one which he correctly spotted provides an immediate proof. So this is a result from topology. So there is a compact set. Compact, it all takes place in n-dimensional space. So compact is that it is enclosed in a ball, and convex means that if you connect 2 points in this set, then all the intermediary points are also in this set. A ball is a good example, or some cone, for example. So now this function phi maps elements of this set into subsets. So to each element it assigns a set. And now there are 2 conditions for this function. One is that it maps every element to a non-empty set which is convex, so such that when you connect 2 points, then all intermediary points are in this set. And moreover, it is in some appropriate sense continuous. So if you have a sequence of such numbers xi, yi, which converges to a specific point xy, and suppose that each elements in this sequence satisfy this property that yi is in the image of xi, then it also extends to the limit, namely y is in phi x. And his claim is that there exists a point which is in its own image. And Nash used this result by finding a function phi which is associated with every game. And this function phi is constructed in this slide. It is the function best. So this function is constructed in 2 steps. First, we, for each player, create a function best I, and this function, given a joint strategy of his opponents, assigns to it a set of strategies of player I. By strategies, I now mean mixed strategies. So best I is the set of best responses, and this is defined here. Oops. I think the battery is gone, but it doesn't matter. It is best I is defined here. So here is the definition. So best I takes a vector of strategies of the opponents and assigns to it the set of best responses, which mathematically is simply the set of such mi prime for which this function attains maximum. And then we make a Cartesian product of these functions, which is defined at the bottom. So this is the function here, best m. So given a joint strategy m, we take for each player his best function. So this is the set of best responses to what the opponents chose, and we take a Cartesian product of these sets. And then there is a very simple observation which really follows directly from definition, that Nash is M is a Nash equilibrium if and only if M is in the image of best M. Why? Because if it is in the image, it means that each component of M is a best response to the remaining strategies. And that's exactly the definition of Nash equilibrium. And it's also, of course, in the other direction. So the construction, there is not a single symbol omitted here. It is a full definition of the function best. What remains is to show that this function satisfies the assumptions of the theorem of Kakutani. And this is also easy because this is the consequence of the definition of mixed extension. These PI functions are continuous. They are defined in such a way that when you slightly change the values, or let's say this arguments, then the payoffs also will only change slightly. And this means that certain theorem can be applied from calculus or from analysis, namely that when we have a function which is a continuous function from a non-empty compact set, then it always has a maximum or minimum. So this is called, if you followed analysis, Weierstrass theorem. And this is simply a theorem which is very often used in analysis. It's very important. For example, a continuous function on a closed interval attains a maximum or minimum. Here we use it to be sure that in this definition, this best M is non-empty. This was one of the conditions of Kakutani theorem. The other was that this convergence of these sequences is here also satisfied. It was this condition 2, and this turns out to be also very easy to check. So as a result, both conditions are satisfied for this function best. And as stated in the last line here, a fixed point, so an element which is in the image of this function best M, if it happens to be the case, then it is Nash equilibrium. So by Kakutani theorem, such fixed points exist. Conclusion, the Nash equilibrium exists. End of the proof. Now, if you are interested, then here is the original paper of Nash. So it starts here, and now I move on. It is one page. So it was submitted in 49. Now I move to another page. Kakutani, you can see now here, the last line, Kakutani. End of the paper. So the paper is one page long, and as you see, there are no formulas. He just wrote it, but he wrote it in such a way that it's very, if you read this paper, you'll have no problem to make this proof formal. But this gives you an idea that certain brilliant contributions are strikingly short, and that's what makes it so powerful. I concluded one part of my lecture. Now the other part remaining is to tell you what von Neumann proved 20 few years before Nash. And in fact, there is some story, it's mentioned in the book, which we discussed, this beautiful mind, that when Nash, as a student, established this result, he felt that it's important, so he went to the office of von Neumann, and von Neumann found it totally uninteresting. So it shows that even great people can make serious errors of judgment. Now, what von Neumann did, in retrospect, is he established that there are Nash equilibria in mixed strategies in zero-sum games. So this is what I will now explain to you. You could say it's just a special case, sure. But because it's a special case, then more can be established. So I will first introduce a concept of security strategy, because it's very important here. And then we'll discuss a generalization of zero-sum games called strictly competitive games, and then we'll focus on zero-sum games. So security strategies, they have nothing to do with two-person games. It can be introduced for n-person games, and the best way to look at it is that you are an absolute pessimist. You just want to know how much there is a game. And somebody asks you, what is the minimum payoff you are guaranteed to obtain? So the way to look at it is that the other players form a cartel, the objective of which is to punish you as much as possible. So they will choose such joint strategy minus yours that you will have really a bad choice. So how do we model this intuition? Given my strategy as I am a pessimist, so I assume that they chose such a sequence of strategies that I get the lowest payoff. So this is this formula. So for strategy SI, we assume that bad luck happened. They selected such strategies that my payoff is the worst. So knowing this, because I'm a pessimist, I now protect myself against this situation by choosing the strategy which causes the least damage. So I know what is the minimum payoff if I choose strategy SI. So now I choose that strategy which still gives the highest payoff. So I maximize the function Fi. So the maximum of this function is called a security strategy. It is a guaranteed payoff which you can get no matter what. And now you have a formula which will come back in this von Neumann theorem, max-min. It comes from the fact that when you write out this Fi of S star sub I, then you maximize a function which is defined in terms of minimum, so you have max-min construction. So that's where this max-min enters the picture. And this is an abbreviation. It's a number, yes? So now there is a game in which you can see the use of security strategy. So it's called chicken game. So if there is a story behind this game, but it's not so relevant. So this is the matrix of the game. Now you can see that there are two Nash equilibria here, namely T and R, where the first player gets a lot, 101, and the other 1, and vice versa, symmetrically. Now suppose you play this game. Now, it is a very serious problem because you would really, suppose I'm a role player, so I would like to choose 1 because then I think the game will end up in Nash equilibrium the TL, But I mean, it's a naive thinking, because the other person will probably for the same reason choose L, and then we both get 0. So there is, in some sense, these Nash equilibria are vastly unjust to the other player. So one player gains a lot, the other very little. So it is more natural to protect yourself against the fact that the other player wants to maximize his payoff by choosing the strategy leading to Nash equilibrium. So it is more responsible here to settle for slightly less. And this you do by choosing the other strategy. So if each of them chooses B, the second strategy, so B and R, then the payoff will be 100. And in fact, these two strategies are security strategies. Namely, for B, the guaranteed payoff, the worst one, is 1 for player rho, and whereas T, the worst payoff for him is 0. So by definition, these are security strategies, and they lead to an outcome which is not a Nash equilibrium, but it is a meaningful outcome. Now, in zero-sum games, it turns out that all Nash equilibria are collections or combinations of security strategies. I sort of try to motivate them by an example. So now we consider max-min and min-max. So I consider now a dual kind of construction. Small fi was defined on strategies of player I. Now capital Fi is defined on joint strategies of his opponents. And what I do is the following, that suppose that I know which joint strategy will be selected by, which strategies will be selected by the opponent, so they, so to say, move first, and then I can decide. So this tells me how much I will get. So given that they selected S minus I, I'm guaranteed this payoff because I still can select this strategy after them. So then we have this min-max because I cannot predict which strategies they will select first. But if I take the, let's say, want to secure myself against it, then I should take minimum. And this will be the minimum which I'm guaranteed if people say, actually, we'll show you what the other players have selected, and then you move. So the game didn't start, but somebody said, that's how we will play it. So this is the payoff I'm guaranteed to obtain. I do not know which joint strategy they will choose. I have to minimize over all possibilities, but for each of them, I can maximize my choice. So we get a different number, which is min-max. And these numbers can differ. In general, there is only this dependence, that min-max is different than, max-min, sorry, is different than min-max. Here is an example that, in fact, this can be strictly less. So I will illustrate on this example how to calculate these numbers. So we have a game. I only focus on the first players. I do not display the payoffs for the second player. So I add a row and a column. The row F1 is a function which is associated with player 1. So it adopts the strategies of the other player. But I do not know what the strategies it chooses, but I, for each case, want to protect myself by choosing the maximum. So the F1 tabulates the maxima in the columns. So these are the consequences. So if F1 is applied to strategy L, which is the strategy of the opponent, then I'm guaranteed to get 6. If he selects M, then I'm guaranteed to get 4, and so on. Now, the small f function is the function which takes this pessimistic approach from the beginning. It says I can at least get 3 if I select strategy T. because this is the minimum which I will get. For B, the minimum is 1, and we completed this calculation. So now the max-min is completed by just calculated maximum and minimum. So here, small f1 leads the maximum is 3, whereas the minimum of capital F1 is 4. So this explains why max-min is smaller than min-max. Max-min was this first expression which we get, which was maximum of the small f function. So this can differ. But as I said, it will not differ for zero-sum games. But people notice that these results of von Neumann can be presented in a slightly more general way, not necessarily zero-sum games, but games which are called strictly competitive. So the idea is that if, for two players, if I am better off, then the other one is worse off. And this is exactly what is stated there. If I have two joint strategies, and I, being player I am better off in S, then the other player minus I is worse in S. So by negating it, you get this perhaps more intuitive statement that if I improve my payoff by considering that we should rather end up in S prime, then this is the same as saying that the other one will get worse off. So our interests are, is written, diametrically opposed. Here is an example of such a game. So let's check. Suppose that we consider 3, 4, so this TL with the other corner BR. So if we move from TL to BR, then player 1 gets worse off, correct? From 3, his payoff drops to 1. But for player 2, it goes up from 4 to 6. So you can check for all other combinations that it's the case. So this is an example of a strictly competitive game. And a special case of such games is a zero-sum game. Zero-sum game, and the typical example is rock, paper, scissors game, which before the rise of internet, children sometimes played it. And the game is defined by 3 rules. So each player has 3 strategies to choose a rock, to choose scissors and or paper. And the rules are that the rock defeats, so breaks the scissors, scissors cut the paper, and paper wraps the rock. And now if you define such a zero-sum game, then it is enough to provide the payoffs for the first player, because for the other one it will be minus this. So this is the so-called reward matrix, and here is its illustration. So if in this game, if you choose as the first player R, so this was a rock, and the other one chose paper, so paper wraps the rock, so your payoff is -1. And if both of them choose the same, then the payoff is 0 for both of them. So this is an example of a game which is a zero-sum game. And now let us see what we can say about games which are strictly competitive. So von Neumann presented these results directly for, first of all, zero-sum games, and second, he expressed it only in mixed strategies. Now, when I tried to understand this, I looked into various expositions, and I had a problem because these things, some parts have nothing to do with the fact that there exists Nash Equilibrium, and others have nothing to do that one talks about mixed strategies. There are some general implications which are here. So I somehow, to understand better, I put them together, and I obtained these 4 points. They have not, there is the word mixed is not mentioned here. It is true for all games. So first, the first 2 points show that there is a equivalence that a game has Nash equilibrium, a strictly competitive game, if and only if there exists an equality between this max-min and min-max for both players. So this is first thing. The second is that if you have a Nash equilibrium in such a game, then payoffs are always defined in terms of this max-min. So it is this guaranteed payoff you get if you are a pessimist. So this is the guaranteed payoff which you can obtain in a game. And moreover, all Nash equilibrias in this game consist of pairs of security strategies. This can be intuitively explained as follows, that the game is strictly competitive. So it is true, this assumption that the other player is out to destroy me, because it is the same as his attitude that he wants to maximize his payoff. Because our interests are diametrically opposed, then his intention to maximize his payoff is exactly the same as his intention to minimize my payoff. So I am right in being paranoiac and resort to security strategy. And if both of them resort to security strategies, then it will be a Nash equilibrium. But it can happen that such a game has no Nash equilibrium. So the point is, that's why you need mixed strategies. But there is a special case which von Neumann was studying, namely if the game is zero-sum game. Let me go back. I'll give you an example. This game is this game, yes. This is a game where max-min and min-max are not equal. So I can fill in this matrix of this game by numbers so that this game becomes strictly competitive. Any proposals? Exactly, just to make it zero-sum, correct? So if I do this, I obtain a game for which max1 is smaller than min-max1. So, with the knowledge of the information on 4 slides further, this game has no Nash equilibrium. Because I stated there that Nash equilibrium exists if and only if for both players this min-max and max-min are equal. So we here have a situation that there is no Nash equilibrium. So now we move to this result, and in case of zero-sum games, this min-max and max-min of different players are just, one is the negative of the other. So in fact, if one equality holds, then also it holds for the other player. So we can make a more compact statement for zero-sum games and say that a Nash equilibrium exists if and only if for the first player, max-min equals min-max. And this was an example on this previous slide of a game which is zero-sum. You allowed me to complete the payoffs, for which there was no Nash equilibrium because this equality did not hold. But when it holds, there is a Nash equilibrium, and then the security strategies which form a Nash equilibrium, they are called a saddle point. And now I come to this kind of informal shape which we discussed, that the saddle point has to do that the saddle, as I mentioned in the first lecture, consists of this part and that part. So maximum of that structure turns out to be minimum of this one. And this is therefore min-max, max-min. And at the intersection, you get the point where it equals. And these are those equilibria. So that's why one calls them saddle points. And the max-min is, in that case, the payoff in a Nash equilibrium. And therefore, this is associated with the game. It's called the value of the game. So to summarize, we now still need to go back and say what actually von Neumann proved. So here is an example of a game first, where we can compute its Nash equilibrium by focusing on max-min and min-max. So here I change these numbers in such a way that the equality holds. So this is a reward matrix. So before I did not have these notions, I had to put these bars or the hyphens where I did not fill in the values for the other player. Now we know that it will be minus, so we just settle for reward matrices, and we compute the entries for this capital F function and the small f. So for small f, we take this pessimistic approach. So for strategy T, for player 1, the value will be 3. That's what he's guaranteed to get. If he selects B, then the guarantee is 1. So he should choose T, correct? Because then he will get 3 at least. Now, capital F1 is the situation, what happens to player 1 if the other player moves first. So if the other one moves first and he chooses L, then I know, so I should choose B, so I get 6. So this explains this entry here. Here it is the maximum is 3, here the maximum is 5. So now we take a minimum of capital F1 because we do not know what the other player will choose, so we get 3. And this turns out to be the maximum of the row of the column where small f is displayed. So there is equality. From this theorem, there is a Nash equilibrium. Where is this Nash equilibrium? In the security strategies, and you can check which are the security strategies. It is T and M. So this is the only Nash equilibrium in this game. So now let us move to the minimax theorem of von Neumann. So he proved that for a finite zero-sum game, if we move to its mixed extension, then this formula holds. So this is nothing else than the statement min-max from the previous slides applied to the mixed extension of this game, and the same with max-min. So he proved that this equality holds. Now, if you go back to the previous slides, then you may remember that this was the condition. It is equivalent that the game has a Nash equilibrium. So since this holds, then this game has a Nash equilibrium. So the precise proof requires one small observation. If we start with a zero-sum game, we take its mixed extension. The mixed extension of this game is still a zero-sum game. It's very easy to check. And for this mixed extension, we apply the previous theorem, which says that for a zero-sum game, the existence of Nash equilibrium is equivalent to a statement that min-max equals max-min. And von Neumann proved that this equality holds, so we know that there is Nash equilibrium. And from this previous general result, which has nothing to do with mixed strategies, we also know that all Nash equilibria are of a certain form, namely that they are the combinations of security strategies. So this is the essence of his result. And I will now provide you with perhaps an additional result by hand waving. And this is a very simple result, which is called Interchange Theorem. So I will provide first as a backup the slide which I will be using, which is this one. So note the difference between what is written here and on this slide about the result of von Neumann. Mixed strategies are not mentioned, and it's also not mentioned that Nash equilibrium exists. We only relate the existence of Nash equilibrium to this equality of max-min and min-max to both players. If it is zero-sum game, it's enough. On this next slide, it was stated that it's true for player 1. So now you should look at the last point. All Nash equilibria are combinations of security strategies. So there is an interchange theorem. Now I will show you this. It's both the result and the proof will be by means of hands. So you have here one Nash equilibrium in zero-sum game, or actually the game strictly competitive is good enough. And here is another Nash equilibrium. So we have a rectangle. When I move here, then I change strategy of the column player. If I moved here, I only change the strategy of the row player. So we have those two joint strategies. I say this is Nash equilibrium and this is Nash equilibrium. That's my assumption. Now, for you, I leave now a problem. Prove that these two corners of this rectangle are also Nash equilibrium. Any suggestions? Do you understand the result? Is it clear, the result? Or I should draw it on the blackboard? You have two joint strategies, so there are two players, yes? So it can be displayed on such a bimatrix, which we used all the time. So I choose two entries in this matrix. Now I create a rectangle by just making these lines horizontal and vertical, and I have a rectangle. In this rectangle, I talk about two corners. There are two other corners. So now I'm telling you, prove that these other two corners are also Nash equilibria. Do you, at least do you understand the problem? Yes? Okay. So who volunteers to prove it? Look at point 4 behind me. Security strategy. Yes, exactly. Because look what happens. If I take another corner, then what are its entries? Both entries are security strategies because this strategy is still the same. It was the security strategy, and this strategy changed from this one to that one, but this one was also security strategy. Because the point is that Nash equilibria consist only of security strategies. So if I replace in a Nash equilibrium one entry for one player by another one, which also is a security strategy, I still get Nash equilibrium because all such combinations are Nash equilibria. You get it? So if you say that the Nash equilibria are exactly the same as pairs of security strategies, then it has a consequence that I can form arbitrary pairs. So if I have two such pairs, I can exchange the components in them, and then I get those two corners in this rectangle. So this is called interchange theorem. So if somebody tells you, here is a result, take a strictly competitive game, take two Nash equilibria, exchange the strategies, you get two new joint strategies, prove that these are Nash equilibria. It doesn't look so obvious, and in general, it's of course false. The reason it's true is because of this point 4, that these security strategies are the only ones which players choose in Nash equilibria. So the result is that these are exactly all Nash equilibria of this game. Okay, so now the final thing to summarize is to compare this what von Neumann did with the result of Nash. So he proved it in 1928, and as I mentioned during the first lecture, if I'm not mistaken, Nash was not born yet. So of course, Nash equilibrium did not have a name. So he called this, I think, equilibrium point. This is not a simple result. And he did not prove it using Kakutani theorem, which is from 1941, correct, or 42. So he used a different technique, and he used something called Brouwer's fixed-point theorem, which is easier to understand and which is more known, which is essentially that if you have a mapping from a ball, say, to itself, then there is a fixed point of this mapping. And this is a beautiful result established by a Dutch mathematician Brouwer at the beginning of 20th century. So this result was known to von Neumann, and he used it to prove his result. And he provided also some other proof later, but the essence of it is that he used this only to his own situation of zero-sum games. So from modern perspective, we can say that he used Brouwer's fixed-point theorem to prove that these games have Nash equilibrium. But he also established more, because he also established that in these games, all Nash equilibria have this very special form, namely are combinations of security strategies. Now, Nash generalized it by one aspect of it, because he studied arbitrary games, and this was not so well known at that time. There were some games like this Cournot competition game. So there were, if I recall, Cournot had only 2 players. So it was not very common to study games of more than 2 players. So this was first the change. The other was that there is no meaningful concept of a zero-sum game for n players. It just does not bring any information that these payoffs become zero, the sum of them. So as a result, Nash theorem was obtained by abandoning certain restrictions which von Neumann took, and still Nash obtained this result that the game, mixed extension of the game, has an equilibrium. But of course, certain concepts did not apply anymore. So security strategies do not make sense in the general context, in the sense that they do not have any connection with Nash equilibria. So this generalization, as always, allowed to improve some results at the cost of abandoning some others. So these 2 results belong to the most important theoretical results of game theory, and they influence the course of game theories. I'll mention just one point, that in economics, people study various games. And then, of course, they are interested to check whether these games have Nash equilibria. So Cournot competition game is a game in which there is Nash equilibrium, and this is an equilibrium in pure strategies. And the games have the property that the payoff functions are continuous. So after Nash result, people notice that it is not only the case that Nash equilibria exist when you consider mixed extensions, it is also the case if you have compact sets and continuous functions on it. The same argument which I used here applies because you just appeal to the Kakutani theorem. So this was first extension. So this was somebody, one of the people who did it is called Debré, and he also, for some other contributions, also got a Nobel Prize in economics. But there are other games for which it is not the case that the payoff is continuous. And such a game you will find in one of these articles on selfishness level, more specifically. It's called Bertrand Competition. So Bertrand Competition is a different game than Cournot competition in the following. In Cournot competition, the players decided the level of production, how much to produce, and this affected the price. In Bertrand competition, the players simultaneously choose the price of the identical product which they sell. So now look what happens. Just let's focus on two players. So if they choose, both of them happen to choose the same product, which they say will be the price of the product, if each of them chooses the same price, then they will split the market in half. But if one of them chooses a lower price, then he will conquer the whole market and the other will sell nothing. So now suppose that we slightly change the price and we slowly move it up, and then in the limit, this price will become equal to the price of the opponent. So the payoff function, this is my strategy. So I change the strategy continuously, but the payoff jumps from 0 to half of the market. So in Bertrand competition, the function is not continuous, the payoff function. Therefore, you cannot apply to this game the general result, even this result of Debré about existence of Nash equilibria when the payoff functions are continuous. So people study such cases and come with specific conditions which those payoff functions have to satisfy to get still a conclusion that a Nash equilibrium exists. So this becomes more and more involved topology. So new results are often obtained by people who study topology. So this is one direction which is almost exclusively the domain of economists. Now, what do computer scientists do? They take a game and they want to compute the Nash equilibria. And the problem is that I told you, if I give you a Nash equilibrium mixed strategies, it is easy to check. I mean, easy. It is a problem, a finitary problem. I only need to check the deviations to pure strategies. But we know by Nash theorem that such a mixed extension of a game has a Nash equilibrium. Find it. Now, it turns out that this is a complex problem, and there is a very important line of research which resulted in establishing complexity of finding Nash equilibria. And this is a problem which is complete in a certain complexity class called PPAD, which people suspect that it is not polynomial. So the outcome is that computer scientists contributed to this area by showing that in general it is difficult to find the Nash equilibrium. And the first inkling that it may be so was already found by Nash, who found a game for which the Nash equilibria are only exist only in such flavor that the probabilities are not rational numbers. So this already shows, and this was a game of, if I recall, 3 players. So computer scientists study this complexity, and then, of course, you have a lot of different, let's say, intermediate results, some games for which you want to find Nash equilibria in a simpler way. That's where this potential function is helpful. So it is an area which is driven by 2 considerations. One is in economics to model certain phenomena by formalizing using a game, and then to study the discrepancy between social optimum and Nash equilibrium. And in computer science, the considerations typically are take a game and try to find its Nash equilibria or prove that it's difficult. So these 2 developments proceed hand in hand, and the outcome is an area with quite an impressive line of research, which is called algorithmic game theory. So at these conferences, both computer scientists and occasionally economists show up, or vice versa. There is an important conference on game theory organized by economists where some computer scientists are invited for a lecture. Okay, so I hope that I gave you at least some idea what this area of strategic games is about and how one can use them to model various phenomena. And perhaps from now on, when you read in newspapers some claims, then you can figure out that some of them truly are nonsense, like with this prisoner's dilemma. What I mentioned, that the director of a hospital said that he faces a prisoner's dilemma. And also, one can sometimes be more skeptical about some statements which are not backed up by any arguments. Game theory provides you with some tools to analyze some statements, but of course, only part of them. Okay, so I think I reached the end of this course, so thank you for your attention, especially for coming on Saturday. So I hope it was of interest to you. Thank you.